wow, this is so exciting. We are really happy to be here with all of you on this webinar to talk about how we design for 6 gigahertz and using Ekahau. What's really important to know is that actually we can't talk all about 6 gigahertz in just one webinar. So what we're going to be doing today is the first webinar out of a series of webinars where we are going to be unlocking and explaining everything about 6 gigahertz. So today we are particularly focusing on design for 6 gigahertz, but make sure you stay tuned for all of our upcoming webinars as we're going to be taking you through all of the key things about 6 gigahertz. And we yeah, what you might want to say, like the summer of 6E. So that's why myself and Mac, we're kind of getting in that vibe to catch that new wave. So we're really excited to be here today with you all. And who are we? Well, you've got myself and Mac here as always, and we are the directors of ECSE and product marketing over here at Ekahau, and our fantastic, amazing psychic Stu that kicked us off for this webinar today. He is here as well. So I actually have a question, Mac, for you. So one of the things we've seen and come up quite a few times is 6 gigahertz and Wi-Fi 6E the same thing?
That's a very good question. So it might be a little bit confusing because we have Wi-Fi 6, Wi-Fi 6E, 6 gigahertz band. It might be mixed up in our heads a little bit. So let's clarify it very quickly. So 6 gigahertz is a frequency band like 2.4 or 5, just higher frequency. And Wi-Fi 6E is IEEE 802.11ax in 6 gigahertz band. So today, the newest is Wi-Fi 6E, latest and greatest, but a few years from now, it will be Wi-Fi 7 still in 6 gigahertz band. So it won't be like 6 and 6, it will be 6 and 7. So I hope this clarifies things a little bit. So let's move to the next slide. This should be clarifying things even more. So guys, we have standardization bodies, and IEEE, it's an institution with the brightest minds available in humankind, and they are creating these beautiful standards. They get together and they produce a few thousand pages of technical content where they describe how things should click together, what goes where, what is what. And then after they have all the amendments and all the different things that build 802.11, they close a standard. So the newest standard is IEEE 802.11 2021, and this includes 802.11ax and all the older generations and amendments as well. So as 802.11ax defined by IEEE, we have Wi-Fi 6 and Wi-Fi 6E. But these two names, they are not defined by 802.11 standard. They are defined by Wi-Fi Alliance. So that's another body that tests interoperability between Wi-Fi devices. So if you have Wi-Fi 6 certified device and Wi-Fi 6 certified client, you know that these two devices will be able to work together. So numbers like Wi-Fi 4, which is N, 5, AC, 6, AX, 6E, also AX, but in 6 gigahertz, E stands for extended. They are just there to make it easier for us, normal people, to understand the generation of Wi-Fi instead of having to remember N, AC, and AX. And now, Matt, talk us through the reg bodies. What is it?
Yeah, so probably another standard organization that we really need to be aware of is the regulatory bodies. So depending on where you are in the world, you're going to have different regulatory bodies, which means you have different rules for things that you can do around transmitting powers, different rules for indoors, different rules for outdoors. And you have different channels that you can use, which on a webinar where we're talking about how to design for 6 gigahertz, this is really important that we understand that depending on where you are in the world and which regulatory body that you fall under, you're going to have access to a different amount of channels that you can use for your 6 gigahertz designs. So it's really important that we understand this. So always please do make sure you check with your local regulatory domain around the rules for your where you are. So yeah, we're going to show you as well inside of Ekahau later how you can change your preferences for the regulatory domain so you can see those different types of channels. So it's really key that we understand this.
Okay, And now, in order to appreciate the 6 gigahertz band, let's spend a second or 10 talking about 2.4 and 5. So you can see these beautiful squares that represent the number of available channels across multiple different bands. Starting with 2.4, we have just 3 non-overlapping channels, and it is not too much, guys. We have 80 megahertz of usable spectrum, but in the real world, we are using just 60 megahertz, so just 3 non-overlapping channels. In 5 gigahertz, we are going up to 25 non-overlapping channels, and it's a big deal on 5 gigahertz versus 2.4 because you can have more radios in the same geographical area serving clients, adding more capacity without adding contention. But now with the rise of the new applications like AR and VR in the enterprise space on top of voice and video, typical conferencing, plus browsing, plus Office apps, we need to have more and more, not only throughput, but also less and less latency. And with increased contention, it's getting very difficult to achieve with 2.4 and 5 gigahertz bands. So 6 gigs, it allows us to change it a little bit, doesn't it, Matt?
It certainly does, Mac. And I mean, if we just take a look at for the US, we're getting it. Well, I say we, I'm not in the US, you in the US, you're getting an additional 1.2 gigahertz of spectrum to use, which is an insane amount of additional frequency to be able to use. So that is going to allow you to have up to 59 non-overlapping 20 megahertz wide channels. Whereas us in the EU, we're getting an additional 500 megahertz of spectrum, which is still amazing to get that additional spectrum because like Max said, with the additional amount of devices coming on the market with Wi-Fi and how all businesses pretty much are going wireless first, businesses run on Wi-Fi, and we're going to have these new futuristic applications, these virtual reality, AR, goggles, and all of these kind of things coming on board to start using Wi-Fi. So to get this huge additional chunk of spectrum is going to really be the future of Wi-Fi. Let's be honest. So,
but we say enterprise, right? But in my house, I have like close to 80 devices on Wi-Fi now. So even I would benefit from 6 gigs massively.
Yeah, but not everyone's quite as crazy as you, Mac.
I know.
Okay. So the first step in our 3 steps to great Wi-Fi every day, it really is still remains the same, that a great network starts with a great design. And how do you get to a great design? Is by gathering your requirements. So just like Max said, if you're designing for 6 gigahertz, then we still need to understand what is the environment we're designing for? What is the desired business outcome? Are you designing 6 gigahertz Wi-Fi for an office that's going to be using voice and video? Or are you designing for an office or an event space that's going to be using lots of virtual reality headsets, goggles, applications? Because that's going to really change how you would do your design. And I was thinking about this webinar over the past few days, and I was thinking about a customer that we did a validation survey for quite a little while of time ago now. And I was reviewing this validation survey of a office which was in New York, and this office happened to be on the 20-something floor in this multi-tenanted building. And they'd sent over, someone else had done the survey, and they'd sent over the file to us and asked us to review the file and to come back with some suggestions on how we could improve the Wi-Fi there, because they said that they were really having a bad time on the Wi-Fi and it wasn't working too well. So I was analyzing the data in Ekahau and I was having a look through the file, and this is when I got my new high score. And when I say high score, I'm talking about the amount of channel contention that I found on this file. And on 5 gigahertz throughout the whole entire floor, at any given point, I could see that we were able to hear up to 56 other Wi-Fi radios access points, all trying to use the 5 gigahertz frequency band all across the Uni 1 and Uni 3 channels. And I remember I was analyzing this survey file and I sat back in my chair and I thought, what can I really go back and say to this customer? How can I fix their current Wi-Fi? And I just remember sitting there thinking, man, these guys really need 6 gigahertz, because what do you do if you've got 56 other access points all trying to share the same channel at the same time? If you just let's say there was 3 client devices trying to to connect to some of those access points, that puts that contention level up to like 150 devices, all pretty much trying to share the same channel at the same time, which is yeah, it's not going to work too well when we know that contention is pretty much the #1 killer in Wi-Fi. So that made me laugh. What I would love to know is, everyone that's on the webinar today, what is your high score? What is the highest amount of code channel contention that you have seen in a project file for when you have analyzed survey data? So use the chat, let us know what the craziest number you've seen. I'll be so shocked if anyone's had higher than 56. I almost couldn't believe it, but when I took into consideration all of the multiple floors that were in the building, and also all of the other buildings that were surrounding this building, the access points from neighboring buildings were blasting into this office. So that's where we could just hear all of these radios. So
this is absolute madness. What I've seen in central London was 404 APs on channel 1 on 2.4 gigahertz from one area of the building. So but that's 2.4, so that doesn't count, I guess.
Yeah, I suppose 2.4 is that's still quite high for 2.4, let's be honest. But yeah, 5 gigahertz seeing 56 on the same across multiple channels on 5 gigahertz, that kind of blew my mind a bit. So that was insane. Anyway, let's yeah, why don't we move on to this next slide then? So
yeah, but before we move on, let's quickly add on that, you know, just having 6 gigahertz band, it doesn't just improve life for 6 gigahertz capable clients, because you will have 2.4 and 5 gigahertz clients exactly where they were, and then tri-band APs, and some of the clients will start using 6 gigahertz bands, and by doing it, they are not using 2.4 and 5. So it will be easier for legacy devices. They will have more airtime available for them because there is less devices on that band. And also on 6 gigahertz, we don't have to support any legacy devices because there is no legacy devices at all. Wi-Fi 6E is the first generation of Wi-Fi working on 6 gigahertz band, which is absolutely smashing, and it will make a massive difference when compared to older bands.
Yeah, absolutely. And what we wanted to talk to you about today was something that's called free space path loss. And what this is the energy that is being emitted from the radio inside of the access point. What we're talking about in this example here is what happens to that radio wave over distance. So how much energy does it lose? And we also use something which is called the inverse square law, which basically means every time you double the distance from the original source, you have 1/4 the power. Now, to get to 1/4 in Wi-Fi, we have to -3 and -3. So that's going to be -6 dBs. But let's just take a look at what happens here. So we've got an access point that we can see on the left-hand side, and we are looking at what happens over distance. So it's going from in the first 1 meter. Let's take a look at the 3 different frequency bands. So we've got 2.4 gigahertz in orange, we've got 5 gigahertz in green, and then we've got 6 gigahertz in yellow. So in the first 1 meter distance from the radio inside of the access point, we lose -40 dBs on 2.4 gigahertz, -47 on 5 gigahertz, and -49 on 6 gigahertz. And then what happens when we go from 1 meter to 2 meters? That means we're effectively doubling the distance. So we're now going to have 1/4 of that power. So if we had -40 at 2.4 gigahertz when we're at 1 meter, when we go to 2 meters, we're going to subtract 6 dBs because that's how we get to 1/4 of the power. So it goes down to -46 dBs. And for 5 gigahertz to -53, 6 gigahertz -55. And then when we double the distance again and go from 2 meters to 4 meters, we subtract that 6 dBs. So the reason why this is key and important for us to know is because this is the logic that we use when we're doing our predictive modeling inside of Ekahau. And I'm going to let Mac explain to you about something else that we do with our predictive modeling.
Totally. So now what happens when a wall is introduced? Guys, like look at the 4 meters mark. Let's say on 6 gigahertz, we had neg 61 dBm, okay? And now when we move to 8 meters, what would we expect to see there at 8 meters? If it was 61 on 4, we double the distance to 8. We know now that when we double the distance, we quarter the power. So quarter the power is half and a half again. So it's -6. So if we had next 61, double the distance at 8 meters, we should see next 67. But if we introduce a wall that attenuates on 6 gigs 3 dBs of a signal, then this will be taken out of that RSSI at 8 meters. So now we are looking not at next 67, but next 70 instead. It's as simple as that. So now the free space path loss and attenuation of walls and attenuation areas, it's exactly what Ekahau is using by default to calculate how the radio waves will propagate away from a radio. So we know the propagation pattern of an antenna or an AP, and then we use free space path loss plus attenuation to calculate it all. On top of it, now with the addition of AI Pro, we've added also diffractions and reflections to make it even more accurate when it comes to modeling of how Wi-Fi signal propagates.
Exactly, and we I think it's probably about time that we jumped into a demo Mac, so we can show people one of our amazing new features, which is the wall calibration tool, which really helps us get much more accurate predictive models. So why don't I actually get that going right now? So here we go. Our amazing new wall calibration tool can save you so much time, and how it relates to the important part of step 1 in our 3 steps to great Wi-Fi every day. As a part to step 1 with a great design will require you going on site to get an understanding of the physical environment. There are a lot of factors here for us to consider, from accurately validating the scale of your floor plans, looking at mounting locations for your beautiful access points, and of course understanding how the walls on site are going to affect the RF by form of attenuation. The reason why this is such a crucial part of the process is so that you can use this data gathered to go back and update your predictive model with correct and accurate data that you have collected from going on site. Previously, before doing the walls attenuation testing the manual way, it would have consisted of you collecting data by going on either side of the walls that you wanted to test, collecting samples of data, and then manually reviewing the data samples to work out how much attenuation each wall was causing. And now, obviously, if you have many different wall types on site that you wanted to measure, this could be quite a time-consuming process, and let's face it, not that fun of a task either. Well, thankfully, these days are now a thing of the past because of combining the power of AI in Ekahau AI Pro and the Sidekick. We can now do this wall attenuation testing automatically for you with our wall calibration tool. So let me take you through the steps that we need to take and how the tool works. What you can see here in this Ekahau project file is that I have collected measured survey data, which we can see here from these green survey path lines in the file. And we can see here that we're looking at all of the measured signal strength from all of the networks, but I can filter this down to be just my networks, and we can see the coverage coming from these access points. I can turn on just an individual access point, and this is real measured survey data from these access points that were on site. And I also have simulated walls drawn. And I know what you are thinking, that this isn't normally something we would do as part of our regular flow or process by mixing measured survey data with simulated walls, as the walls have no effect on the measured data. They are just for our simulated access points. But stay with me. The wall attenuation values that we have got set right now are the default values of the walls when you start a new project file. The reason why we want to have simulated walls drawn initially with the survey data is because Ekahau is going to use the data collected from the Sidekick and our survey paths, look at our simulated walls that we have drawn, and then automatically calculate attenuation values for these walls. As long as we have collected enough data by ensuring that we have walked on both sides of the walls that we care about, which you can see in this file in most cases we have. There are a couple of ways that we can do wall calibration. And actually the first way that I'm going to show you is by going to an individual wall segment, which I have over here. Let me just zoom in a little bit actually, so we can see a little bit better. So I'm just going to left click on this wall right now. And what you'll see is up here, we can see this wall dry 3 dBs. Now this is the default attenuation value for this wall. But what I can do now is I can right click on this wall segment and it gives me the option to calibrate attenuation. And when I click on this option, notice what happens at the top. So now I have calibrated this wall. You can see it's gone from wall dry as just 3 dBs and it's now applied an attenuation value of different values across the 3 different frequency bands. Pretty cool, I know, right? I'm just gonna undo what I just did by doing Control Z or Command Z, depending if you're a Windows or a Mac user, because I want to show you an alternative way that we can use the wall calibration tool. And that's by going up to Actions and then selecting the wall calibration option. And now this is going to pop up this window where it's going to tell us all of the simulated walls that we have got drawn in this project file, along with their default attenuation values and as well as their proposed attenuation values. And what we can see here is that it's also making proposals for the 3 different frequency bands, so 2.4 gigahertz, 5 gigahertz and 6 gigahertz. So if we take a look at the proposed value changes for this first wall type here, which is an interior office, the default value at the moment is set at 4 dBs and it's suggesting that we go to either 2.5 or 1.5 dBs depending on which frequency band that we are using. And this is a realistic and accurate change for this type of wall in this environment. And then we see that we have another column here which is called quality. The quality column gives you information on how reliable the results are for that particular wall type are found to be. When wall types are assigned the good quality, this means that there has been enough data collected for these wall segments that Ekahau can give a confident proposed value for this wall type, which is the majority of the walls below. And the reason as to why the fire exit doors and the concrete walls are marked as poor is simply because when this survey walk was completed, we did not go into the fire exit stairwells and collect enough data on either side of these particular walls. So the fact that these are marked as poor values is completely fair enough, as we did not collect enough data. We then have the option to apply these proposed changes one by one, simply by clicking on the apply button next to the wall type, or alternatively, we could hit the apply all button at the bottom of the window if we are happy with all of the proposed changes. So I'm just going to hit close now. So what I would do next then is, now that I am happy I have my accurately calibrated walls, I would save a new copy of this file by going to File, Save As, and I would call it something along the lines of predictive model version 1, and then hit save. And then the next thing that I would do is I would now delete the collected measured survey data so that I have a project file with my accurate scale and simulated walls, so that I can now begin building my predictive model. I personally like to keep my measured and simulated data separate. So I'm going to show you now how we can delete our collected survey data, but please do make sure you have got another file with this data saved, as once you delete your survey paths, there is no undo to bring them back. So what we would do now is head over to the surveys option here, and what I'm going to do is I'm going to select all of these surveys. Once I've got them all selected, I can then right click on the survey and then hit delete. And we're going to get another warning saying, are you sure? Because remember, if we delete these, we cannot undo this. So I'm just going to hit yes. And what it's going to do is going to go through the file and remove those survey paths, and therefore in turn remove all of those access points, so we have got no surveyed measured data inside of our predictive model. And then now what I can start to do is start to place my simulated access points on the floor plan. So I can come over to here, pick a simulated access point that I'm happy to use, and I can simply start to place the access point on the floor plan and start to build out my predictive model across all 3 bands, which I am confident that I know that my file has got accurately scaled floor plans, accurately calibrated walls, and this process with the new calibration tool, it really does make my designs more accurate. It removes a ton of manual work, guesswork, but most importantly, time. And I think I'm going to go back to the slides and then hand back over to you, Mac.
That was a good demo. Thank you very much, Matt. So yeah, quite informative, at least for me. I hope everyone else finds it as informative as myself. So now, guys, let's discuss the 6 GHz devices classification. This is, my friends, a new thing. Okay, we didn't have it before. So before we had 2.4 devices and 2.4 GHz, clients and access points, 5 GHz clients and access points. If you had AC client and AC AP in 5 gigs, then it would work, right? Because they're both Wi-Fi certified and it's as easy as that. Easy peasy lemon squeezy. Now with 6 gigs, it's not that easy anymore because there is quite a lot of incumbents. So already existing technology on 6 GHz band, and we have to protect it, right? So we cannot just start using Wi-Fi like there is no tomorrow with super high gain antennas in and out and start interfering with those technologies. So that's why a device classification was introduced. So low power indoor, it's called LPI, low power indoor, will be the main devices class used in Wi-Fi 6E. So what it means is that we are allowed to use, without further restrictions, Wi-Fi 6E inside using LPI class devices, but access points, they have to be physically mounted. They cannot be mobile. They cannot be battery operated. You can still use UPS, of course, but they can't be like a mobile AP devices. They cannot have external antenna slots. So you cannot just attach a high gain antenna and not abide by the rules set by reg bodies anymore. Also, you cannot use Wi-Fi 6E in like trains or planes, on platforms, anything like that. The only exception is when you have a passenger aircraft at 10,000 feet or more, then you can enable 6E radios. That's fine. So that's LPI, and LPI, it supports all 59 channels in States, at least. In Europe, it will be less than that. And then you have LPI clients that can connect to LPI APs. You cannot have any client connecting to any type of access point. So LPI AP supports only LPI clients. Then you have standard power, SP APs, and you can see that you can now use it both indoor and outdoor, and they support higher EIRP. However, it says that it's controlled by AFC. So AFC, we won't dive too deep today into what it is. It's automated frequency coordination. Basically, it's a database in the cloud that knows about the location of existing 6 GHz technologies. And when your access points comes online, it has to locate itself, most likely using satellite positioning system, probably GPS. So it knows its location, its height, it knows its direction, antenna gain, and it will send this information over to AFC, and then AFC will go back to the access point saying that, Mr. AP, you can use the maximum EIRP, so transmitting power level with your gain of, let's say, 10 or 20 or 30 dBm, and also you can use just the subsets of channels. You can't use everything to not interfere with existing 6 GHz technology. And then you will have SP clients that can connect only to SP standard power APs. So SP client won't be able to connect to LPI AP, okay? You probably will see dual clients as well that can connect to both LPI and SP APs, but we think that at this point they will be very rare, okay? So most clients will be LPI clients. And then the last category, devices classification, is the very low power. Very low power can also be operated both indoors and outdoors. The difference between SP is that it doesn't have to ask AFC for permission about what transmitting power and channel to use, but it's not approved in the US yet. It probably will be used faster in the EU, and you will have VLP clients that will be able to connect only to VLP APs. We also expect VLPs to be very rare. And also there is another rule there that says that if access point has an EIRP of whatever level, all the clients, they have to be using EIRP of 6 dBs less than the APs. If the access point changes power, then the client will have to adjust that power. If the client roams to an AP that uses lower power, it will have to lower its power as well. That's how it's gonna work.
Well, I mean, I know we said it at the start of the webinar, but there is so many other new things we have to think about when it comes to 6 gigahertz. So remember, this is why we can't cover everything in this webinar, but over the course of our next few webinars, we will be diving deeper into all of these new things to do with 6 gigahertz to get everyone up to speed. And now we have a poll question. So Mac, if you could do the honors whilst I launch it.
Of course, like always, let the poll read the poll, right? What are you... And again, Matt launches the poll and it obscures my screen. What are you most looking forward to with 6 gigahertz networks? Answer A, higher performance, more speed, less latency. B, more channels to design with, less interference. C, elimination of older, slower technology devices. Or D, shopping for new APs, hooray.
Yeah, we'll let the votes keep carry on rolling in for a few more moments time to give everyone a chance to make sure they can cast their vote. Really interested to see the results on this one. What everyone's most looking forward to is 6 gigahertz. We're really excited for 6 gigahertz. I bet everyone else is too. So it's be really fun to find out exactly what part of 6 gigahertz everybody is looking for. So I'm going to end the poll now so I can share the results for everybody. And here we go. So we can see that there was pretty much one clear winner here, which was to, you know, the more channels to design with less interference. That was a pretty high percentage. And then not too far behind it was the higher performance with more speed and less latency. The one coming in at third was the elimination of the older, slower technology devices. And surprisingly, not that many people seem to be that excited for shopping for new APs. So yeah, interesting.
But I'd like to shop for a new AP.
Well, it's no fun to buy new APs then. I'm looking at the chat as well, and I agree with Jeremy saying that C is challenging even with disabling 2.4. It's been a challenge for ages, so it probably will stay a challenge moving forward.
Yeah, okay. I mean, wow. So people are excited for the channels. What do we have next is the 6 gigahertz channels allocation. And first, we're going to look at the LPI that Mac was just talking to, the low power indoor. And we are looking at the FCC allocation right now. So remember, they're getting an additional 1.2 gigahertz of spectrum that they can use. This means that they are going to be using the upper end of 5 gigahertz all the way through 6 gigahertz to the lower part of 7 gigahertz. So the uni bands that we're going to be using now is Uni 5, Uni 6, Uni 7, and Uni 8 for the low power indoor. So what does that mean then? That means that for low power indoor devices, they can have up to 59 20 megahertz non-overlapping channels. But what can we do in Wi-Fi? We can bond to adjacent radios or channels together, to adjacent channels together on our radios to create a wider channel and create a 40 megahertz wide channel to give us the higher data rates and more throughput, which is, if we want to use 40 megahertz wide channels, we absolutely can. That means we're going to have up to 29 non-overlapping 40 megahertz wide channels. And again, if you want to bond those together, again, that's going to give us 80 megahertz wide and 14 of those for the low power indoors. And then finally, if you want to do 160 megahertz wide channels, that will give you 7. And it is possible to do 320 megahertz as well. But realistically, are we going to see that? Because that would only give us a couple of channels that wouldn't overlap. Maybe in some very small environments or at home, we're going to see that. But what the key thing here is what 6 gigahertz is going to unlock for us. If you look at, let's say, the 40 megahertz wide channels, that gives us 29 non-overlapping channels, which, if you remember, in 5 gigahertz, we only have 25 non-overlapping 20 megahertz wide channels. So even with a double the size of the channel, we have more available in 6 gigahertz. But what we think probably is going to be the most popular and the default channel width is going to be the 80 megahertz wide. We'll explain more about why we think that on our next webinar, but having 14 non-overlapping 80 megahertz wide channels, this is going to be fantastic for those applications that need that higher bandwidth, that virtual reality, AR as well. The other cool thing to think about here and note is that unlike in 5 gigahertz, where we had to worry about radar or DFS, this meant we don't have that same concern in 6 gigahertz, because, you know, in 5 gigahertz, that if you're affected by radar or DFS activity, that can remove a whole bunch of channels for you to be able to use. So this is really, really cool. And that's covering the low power indoor. How about the standard power now? So the SP that Mac was talking about just a few moments ago. So the key thing here is that with standard power, we only use the Uni 5 band and the Uni 7. We're not leveraging Uni 6 and Uni 8. So this means that instead of having 59 non-overlapping 20 megahertz wide channels, it goes down to 41. And for 40 megahertz wide, it's 20. 80 megahertz wide is 9, and then 160 megahertz wide is 4. So that's still an abundance of additional channels and spectrum that we're going to be able to use, which is going to be fantastic and amazing, but just something for us to think about and to consider.
Yeah, but just two things to also add there. With 80 megahertz channels, we will talk more about that in 2 weeks' time, I think, on the next webinar. So even if you have just 14, then it gives you such massive data rates that devices that will be spending less time on Wi-Fi, they will just come in and then send what they have to send and back off, allowing for more devices to access medium when they want it. So even with higher CCI, slightly higher CCI, you still should be able to achieve amazing things with 6 gigs. And with standard power APs, you have up to 41 channels, but you don't have to have all of them, right? Because if AFC tells you not to use most of them, then you are limited to just a few. Just saying. Guys, we have a very good question or questions in our chat, like what is the range difference between 6 gigahertz design versus 5 gigahertz design from David, for example. We had questions about how does designing 5 gigs versus 6 gigs look like. So instead of just doing a dry answer to those questions, let's take a look at a demo instead, shall we? Okie doke, so let's talk about coverage planning. We have Ekahau AI Pro in front of us, but before we talk about coverage planning on 6 gigahertz band, let's quickly clear some things out. So designing Wi-Fi is not only about the coverage, right? Coverage is easy. Primary and secondary signal strength are easy. What is difficult is the capacity. So catering for all the devices that you want to have in a physical space with the number of radios, ensuring that they can access medium where they want to and they need to, depending on what applications they used, in a way where they will be able to access it with low latency, low retransmission rates, and high reliability. So that's difficult, okay? So capacity is difficult. But today we will be talking about coverage. So let me just place an access point on the map. I have selected Extreme Wireless AP 4000, which is tri-band AP, so it has 2.4, 5, and 6 gigs bands inside. And let me configure some channels on this AP and power levels, and we can see that we have 14 dBm across all the bands. Let me actually start with channel 1 on 6 gigahertz band. So it's all defaults, but just for clarity, everywhere where you see colors, it's next 67 dBm of primary coverage or stronger. Everywhere where you see gray, it's between next 67 and next 85. So still, it is considered a coverage. So where you have two APs on the same channel and clients associated to both AP on the left and AP on the right, they will be contending for the airtime, assuming that they are on the same channel, all the APs and clients. And then everything that is in white, it's neg 85 dBm or lower. So it pretty much doesn't matter from the Wi-Fi contention perspective. I didn't want to place a secondary AP. Okay, cool. So let's go back quickly. And let's check the power levels and everything else. I have 2.4 gigahertz, 14 dBm 5 gigahertz, 14 dBm, 6 gigahertz, 14 dBm, and all of those bands, they are sitting on their first available channel. So with those settings, what I would expect to see is 2.4 going farther away from the access point than 5, and 5 going farther away from the access point than 6. Actually see that 2.4 and 5 are very similar. I didn't see that coming. It might be due to the fact that they are using different sets of antennas, they have different radio chains, and they might have different antenna gains. So let's check that out. Actually, EIRP, so the gain, ARP, it takes under consideration the transmitting power levels. They are all the same across all 3 bands, and antenna gain, passive antenna gain, and they're all very similar as well. So coverage pattern from the antennas on 2.4 gigahertz band versus 5 gigahertz band, it seems to be different in a way where 2.4 doesn't cover way more than 5 gigahertz. But let's focus on 5 versus 6. So on 5 gigahertz, we have cell that is that big. On 6 gigahertz, we have cell that is that big. So clearly it is way smaller. And let me make another adjustment. I'm moving from channel 1 to channel 233. And now you can see that the area is in fact even smaller. So why does the coverage change when I switch between different channels in the same band? And actually, understanding free space path loss, so how the signal propagates away from the access point, is crucial here, because it depends on the frequency used and a distance traveled. And the higher the frequency, the higher the loss of energy density when the signal travels away from a radio. Just to try to use simpler words, 5 gigahertz will cover more than 6 gigahertz because it has a lower frequency. So now let's talk about frequencies. So on 5 gigs, we have up to 25 non-overlapping channels. Actually, now I am using regulatory domain set to United States. So I'm talking FCC here. So we have up to 25 20 megahertz channels on 5 gigs. Between the first channel, so channel 36, and the last channel, so channel 165, there are around 700 megahertz difference in spectrum. So they should be covering a little bit more or less. So channel 36, radio on channel 36 will cover more than radio on channel 165. So with that being said, we expect to see a difference between channel 36 and 165 of around 1 dBm. Okay, just 1 dBm difference. Now, let us switch to 6 gigahertz quickly. Now look at that. This is mind-bending. That's on a different level. So we don't have 25 channels. We have 59 channels. Okay, that's a big difference. That's a massive difference. So now between channel 1 and channel 233, the difference is even bigger. So on 5 gigs, we had 700 megahertz difference between the first and last available channel on this specific band. And now we are looking at 1.2 gig, so 1,200 megahertz difference between channel 1 and 233, which translates to roughly 2 dBs of a difference between channel 1 and channel 233 when it comes to the coverage. So look, on channel 1, I'm covering more than I am on channel 233. So now when you consider all the channels on 6 gigs and all the channels on 5 gigs and spectrum separation between them, we start at 5,180 megahertz on channel 36, and then we finish at 7,155 megahertz, so low 7 gigahertz band. And between the first channel in 5 gigs and the last channel in 6 gigs, we in fact have 3 dBs of a difference. Okay, 3 dBs of a difference. So let's validate that quickly. I'm looking at 5 gigahertz channel 36, and I will be looking at 6 gigahertz channel 1. The visualizations, they take a little bit of time, so let me switch diffractions and reflections. So I'm setting it to high instead of max. It doesn't matter here because we don't have any walls, so it doesn't matter if we have high or max visualization set in Ekahau AI Pro. And let's take a look. So with the same power level, same EIRP, around 15, what is it? 15 foot yards, I don't know. We have on that line neg 67, okay? Neg 67. So now when I switch to 6 gigahertz, what would I expect? Around 2 dBs less. So I would expect to see here around neg 69. Let's take a look. So 15, let's call it yards. I hope I'm right. I have neg 70 and neg 69. Yeah, so around 2 dBs difference. So I had neg 67, now I have neg 69, okay? And now when I switch from channel 1 to channel 233, I should have additional 1 dB less based on what we've discussed. So around here, I'm neg 71, I had neg 69, so I've lost even more. Actually, around that spot, I have like neg 70, so I think we are spot on, okay? So it went down from neg 67 on 5 gigahertz first channel on channel 36 to neg 69 on channel 1 6 gigahertz to neg 70 on channel 233. So we've lost 3 dBs, okay? We've lost 3 dBs of coverage. So now let's take a look at a real floor plan with all the walls drawn, and let's see how it would affect our signal propagation in a real environment. So first, let me disable the view of that area. So I don't see the area. Let us see. The walls are so beautiful. I won't be able to sleep now because they are so pedantically drawn. Well done, Matthew. Or was it me? I can't remember. And now let's place the same AP, let's say here. Okay. And my wife is back. And let's take a look at the difference in coverage in 2.4 and 5 and in 5 and 6 gigahertz. Let me switch to 20 megahertz channels here. And now we are looking at 6 gigs and 5 gigs looks like that. Okay, 6, 5. This is low 5 and this is low 6. Now let's switch to high upper 6, which is actually lower 7 gigahertz. And that's how it looks now. So it's low 5, high 6. That's the difference in coverage between two far away channels in both bands, 5 and 6 gigahertz, okay? So now you might argue, with 6 gigahertz, do I need more access points than I did need in 5 gigahertz band? And the answer is most likely you will not require more access points on 6 gigahertz band to get a good coverage, because how would a design look in this office? You won't just use this AP here, and then you won't just place another access point, I don't know, like here, and you see, oh, there is a gap, I will just place like this. Oh, this looks actually quite good when it comes to the coverage, or maybe I will move some stuff around so it's all green. You won't design like that. You will look at the floor plan, and then you will see, okay, I have quite a lot of users here, quite a lot of users here, so I have a big meeting room here. So I have open space here, and I have few people sitting here. This is a drywall, so probably I want to have another access point in that area. Now, I don't want to have these areas underserved, and additionally, I'm just thinking aloud while designing Wi-Fi for this space. I want to have one of the access points, at least one of the access points, to be able to cover this area of the building, so we can leverage 802.11k for more seamless roaming. So this AP will see like an access point that I probably will place in that room. This AP probably might not see the access point placed on the other side of the staircase and lifts and stuff, and definitely not this AP. So I will place another access point probably here, and another access point close to the people, okay? I want to put my radios as close to the client as humanly possible. So another AP here makes sense. I can see that I have like 6 seats, 12 seats. If they have like 1, 2 devices per person, then I wouldn't like really one AP to serve more than like 2 or 3 desks full of clients, assuming that we'll ever see full offices again. So I won't place another access point here. That will give me a perfect coverage, or even here. If I have one AP here and one AP here, coverage is done. But I want to have capacity as well. So I'll probably want to have another access point here and another access point here, and then another access point here to cover that space. And now these access points probably I would prefer them to be a little bit closer to the meeting rooms on the bottom part here. So let me move them very quickly. So it's still very close to all the clients, but also coverage in here is slightly better. And now I am happy with my design in this office. So does the coverage look different? It is a little bit better on 5 GHz, but does it really matter? It's negligible, okay? It doesn't matter. So let's run a channel planner very quickly on 2.4, 5, and 6. Actually, I won't focus on 2.4 too much. And now I will use 80 megahertz channels on 6 gigs because this will most likely be the default channel width. We'll talk about that later. And let's create a channel plan very quickly. And ta-da! We have amazing channel plan. And now this is real, guys. This is real. So 5 gigahertz, it's amazing primary signal strength. 6 gigs, still amazing signal strength. Do I need more 6 gigahertz APs? No. Okay, now let's take a look at secondary signal strength. It's very good on 6 gigs. I don't have coverage somewhere in the corners. Do I care about that? No, absolutely not. It doesn't have to be all green. It has to be practical and good enough. And that's what it is here. On 5 gigs, it's a little bit better. So I would argue that it makes tons of practical difference. And from capacity perspective, this setup with 6 gigahertz on will have more capacity than the same setup, same positions of the access points with just 5 gigahertz or 2.4 and 5, because we simply have 3 bands instead of 2. So we will have some clients on 5, some clients on 6, some clients on 2.4, depending on the configuration. And that's pretty much it, guys. That is actually almost everything that I wanted to show you today. Let me quickly remove the APs. So select all, and I will delete them. Last thing that I wanted to show you for the coverage planning is coverage planning, okay? So you can use a tool that is called the coverage planner. And when I select an access point, it calculates on the fly how would the coverage from different APs look like if I had dropped them here or here or here or here, okay? And it's also band specific, so it will look differently on different bands. And that's truly everything, okay? That's it. Thanks a lot, and let's go back to slides. Matt.
Yeah, thank you very much, Mac. That was a great demo. Let me go back to the slides. Yeah, awesome demo, Mac. That was really cool to see. The difference between, depending on what channel you're using as well, on 5 gigahertz to 6 gigahertz, it affects what the coverage looks like. So that's really cool that we can see that and visualize that inside of Ekahau. And it's great that we kind of covered the reason why that would be happening. And I know the main burning question and reason why everyone was joining this webinar today was because they wanted to find out, what do I do differently when designing for 6 gigahertz? And the answer here is simple. It hasn't changed. You still, when you're designing for 6 gigahertz, you design to meet your requirements. And that's the same for any of the frequency bands or whatever Wi-Fi network you're designing for. You always design to meet your requirements. So if you're designing for 6 gigahertz for an office that wants to use voice and video over Wi-Fi, you're going to design it in this way. And if you're going to be designing Wi-Fi for 6 gigahertz for an office that wants to use virtual reality headsets, or if you're designing for augmented reality in those office spaces where, me and Mac were talking earlier, it's probably not that far-fetched to think at some point in the future we'll put on some goggles and we'll all be sitting around a virtual boardroom and like be able to see and talk to each other in that way. If you're designing for a space that has those types of devices and applications, then you're going to design that differently compared to how you would design for an office that was just using voice or video. Are you designing 6 gigahertz for a shopping center? Are you designing 6 gigahertz for some warehouse spaces? It is all going to change, and no environments are the same. Warehouse A can be completely different to warehouse B. Office A can be different to office B. So when it comes to designing for 6 gigahertz, always design to meet your requirements. So on that note, we are ready to take a couple of questions. Our favorite psychic stew. I can see there's been a lot going on in the Q&A. Are there any questions that you would like to answer live or throw over to us?
I think there's actually one that was, and I think Mac, you highlighted it quickly, was, do I need to be really close to a wall to do a survey, like to gather that data that I want to do for that wall calibration?
Oh, right. So for the wall calibration demo, so yeah,
Like, is it crucial? There it is. I said, is it crucial to walk as close to the wall or to each side to get better calibration?
Yeah, so the more data that you can gather, the better. So it's really important when you're doing these types of surveys with your sidekick, if you want to do that wall calibration, is that you make sure you go on both sides of the walls that you care about. And yes, you want to get as close as possible to the wall that you can, but don't climb on top of tables and over people's desks and stuff to get right up to the wall, just as close as you can. But what it also does, it doesn't just look at just that one segment. It takes the loss of all of the values that that is heard over the period of time during the survey. So it's great to gather that data for that wall, but also you can gather it for other walls that are the similar or sort of same sort of wall type as well. So if you couldn't get right up next to some of the walls, then don't worry, go to another one instead. So yeah, that's a great question and great one to point out there.
I would just add to it, if you are measuring attenuation of a wall manually, then yes, you have to be as close to the wall as possible when you are taking that measurement when walking away from a radio. So you have a radio and then you go to the wall like 10 meters away, you measure it on both sides, you have to be close. When you're just walking around casually, you just have to make sure that you are walking on both sides of the walls, but you don't have to be that close. It doesn't matter anymore. The algorithm, it can work with you walk close to it or not too close to it. It doesn't matter too much.
I think the important thing is to gather enough data so that the AI engine can actually run that calculation, right? So it's got a better understanding. Yeah.
Definitely.
Okay, let's answer another question. We still have some time. So question from Osvaldo. Osvaldo, I hope I pronounce it right. What are the most important drawbacks and disadvantages to have in mind in regards to or when using 6 GHz Wi-Fi? And that is a very good question. And answer number one is it's very difficult to buy Wi-Fi 6E devices still, not too many on the market. And then even considering that you have Wi-Fi 6E infrastructure and you have Wi-Fi 6E devices, I think that one of the biggest drawbacks and challenges will be security, actually, because in 6 GHz you have mandated WPA3. In 5 GHz you don't. So most of the devices in 2.4 and 5 gigs, they will not be able to support WPA3, and therefore even if you have your corporate SSIDs that you would like to have across both bands 2, 4, 5 and 6, for example, you won't be able to configure WPA3 across both of them, because simply even tri-band devices, they won't be able to, all devices, they won't be able to connect with WPA3 even on legacy bands like 5 GHz. And if you want to cater for both all devices on 5 GHz and new devices on 6 GHz, you have WPA2 on 5 gigs and WPA3 on 6 gigs. In this scenario, even if you have Wi-Fi 6E devices that can support both WPA2 and WPA3, they won't be able to roam nicely between those two bands, especially if you have different security mechanisms enabled and this kind of stuff. So I think security will be number one fun killer in this world. A good tip here: never ever have a dual band or now tri-band SSIDs for things that matter. If you use 6 gigs, use 6. If you use 5 gigs, use 5. Don't have it across both.
Yeah, and just one more final reminder that there's so many. That's one thing that Mac just brought up then around, do you configure the same SSID across all 3 bands and the security around 6 GHz? That's a great question, and we're going to dive much deeper into that on our next webinar as well. So if you've got all of these questions in your head about what do I do when it comes to configure my 6 GHz, what channel width should I be using, how is it going to affect my current network, the client devices that are going to be connecting, all of these questions in your head, don't worry, we're going to answer them, but it's going to be across the next series of webinars. So do watch out for when you receive that invitation, and make sure you sign up, because we're going to answer all of those questions for you, because there's a lot of new things to take in and learn with 6 GHz, but it's fun to learn new things. And also, just one other thing to point out as well, that if you really enjoy learning around Wi-Fi and 6 GHz and seeing all the new things in Ekahau AI Pro, you can always get yourself signed up to one of our Ekahau ECSE courses. All of our classes use Ekahau AI Pro, the latest and greatest features, plus has got all all of the theory covered for 6 gigahertz, because we cover it in, across multiple days. So if you're getting interested and excited about that, then please make sure you check out our training so you can get more information on it there as well. So I don't know, Stu, do you have any other questions you wanted to fire across?
I think we got quite a lot of them answered in the Q&A, and I think that's a really good lead up into one of our next webinars of understanding 6 gigahertz. It's a whole new world out there, folks. Yes, Ekahau, we're going to be there for you for sure. Matt, hats off to you for providing that kind of that framework of that training to kind of help us out and guide us through that design today. And I think that we're going to see a lot more, and stay tuned for that. How are we going to work on those SSIDs? Because that's I'm really interested in that. I want to see that next, because that gets me really excited, because those are the challenges that we're going to face, especially WPA3 and how we're designing, because we're taking a whole new realm. And do we use those old legacy devices?
And massive shout out to everyone that is using the chat. We see your comments, by the way. So your suggestion around EduRoam and all the other topics that you put in the chat, we're capturing all of them. We'll try and incorporate all of your feedback that you're giving us during in the questions, in the Q&A, and in the chat. Everything we see, we'll take them away, and we'll make sure we try and answer them in future webinars as well. But just want to say a massive thank you for spending your time with us today. If it's your morning, afternoon, or evening, it was a total blast to have you. We really look forward to seeing you on the next one, where we can start to demystify, unlock some of those new things about 6 gigahertz. And yeah, thank you so much, Mac and Stu, and everyone else at the Ekahau marketing team, for being so awesome. Enjoy the rest of your day. Everyone's loving the shirts. Yes, the shirts are wild. We had to get in the groovy theme, summer of 6E. So we wanted to throw ourselves in there. So maybe everyone else can start wearing some groovy shirts on the next one as well, perhaps.
Yeah, thank you very much. It was a blast of my Wi-Fi life. And by the way, I've seen comments that they call us out for really bad shirts. Actually, I think someone has asked if it's a bad shirt day. So I'm
bad shirt day.
Much, yeah.
Bad shirt Thursday, maybe.
But you know what? I keep it true with sidekick right here.